All right, so in this lecture, we're going to talk about the order in which electrons fill up orbitals in atoms. This is related to the filling order that we talked about in the previous lecture, which you may recall had a couple of unexpected inversions in it. So the filling order is something to know, and we developed a mnemonic device to kind of help with remembering how it works. So we have 1s first, then 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, etc., etc. The full filling order is up here in yellow, as we saw in the previous lecture. So there are a couple of inversions where 4s fills before 3d and 5s fills before 4d, etc., etc. That will kind of help us figure out where electrons go as we fill up orbitals in atoms of different elements from the periodic table. So the first energy level diagram that I want to talk about is electron configurations. Electron configurations are the least informative type of energy level diagram, but they are important and interesting to write because they tell us a lot about what cations and anions might form, for example, when an atom ionizes. So in electron configurations, little numerical superscripts show the number of electrons in each sublevel. And I'm going to illustrate how to write electron configurations with a number of examples. So let's start with carbon. If I look at the periodic table, carbon is atom number 6. It has an atomic number of 6. That means there are 6 protons in its nucleus. And if it's neutral, there must be 6 electrons that are orbiting outside of the nucleus. So that means now I'm going to take the filling order as specified up here and just put electrons into each orbital. I have one 1s orbital that can house 2 electrons, one 2s orbital that can house another 2, and then I have 3 2p orbitals. So I could house up to 6 electrons in those 3 2p orbitals, but I only have 2 left. So the superscripts here should add up to the total number of electrons in the element. So this is the electron configuration for carbon. Let's try another example of a slightly larger element, chlorine. Chlorine is element number 17 rather on the periodic table, and it contains 17 electrons total. So let's write down its electron configuration. It's going to be 1s2, 2s2, and then 2p6. So as far that's 10 electrons. Then I'm going to have 3s2, 12 electrons so far, and then 5 electrons left to put somewhere. I have 3p orbitals because of the multiplicity of p orbitals. I have 3p orbitals. They could house up to 6 electrons. Here I only need to put 5. And now those superscripts add up to 17. So this is the electron configuration for chlorine. So that's neutral chlorine, but what about the Cl-1 anion? Well, the chlorine anion, Cl-1, is going to have 18 electrons. It has just that one extra electron giving it a negative charge in relation to the 17 protons in the nucleus. So that electron configuration is going to be just like the electron configuration for neutral chlorine, except I'm going to have one extra electron in that outermost orbital, in that highest energy orbital. So 1s2, 2s2, 2p6, 3s2, and now 3p6. So if I look for a moment at the periodic table, I have it right here. You can see chlorine on the periodic table is right beside argon, which is element number 18 here. If I look at argon and I want to write an electron configuration for neutral argon, argon is element number 18. So neutral argon is going to have 18 electrons to match the 18 protons in its nucleus. And that means that its electron configuration is going to be identical to that of Cl minus 1. So these two have the same exact electron configuration, and that makes them what's called isoelectronic. These are atoms of different elements that have the same electron configuration. Okay, so isoelectronic just means that they are atoms of different elements that have the same electron configuration. Now, argon, being all the way at the side of the periodic table here, argon is a noble gas, and it's very stable because it has its sublevels entirely filled up. Having all of your sublevels filled up is a very stable electronic arrangement. So this is why chlorine tends to form the -1 anion, because when it does so, it gets a noble gas electron configuration, which is extraordinarily stable. So this is why we tend to see chlorine forming the Cl-1 anion. Let's try a slightly larger element. So iron has, neutral iron has 26 electrons in it. Now I need to spend those 26 electrons so I can kind of fill up the innermost orbitals like this. There go 18 of those electrons. Now I have to look at the filling order carefully, because here I have to remember that there's this weird inversion where 4s fills up before 3d. So when I fill up the electrons in iron, I have to remember that the 4s subshell is going to fill up before 3d. Now I need to, first of all, so far I've spent 20 electrons. That means I have 6 left. I can put all 6 into the 3d sublevel because there are 5 3d orbitals, and 5 times 2 is 10. They could house up to 10 electrons. So I can fit all 6 remaining electrons in there. So one kind of weird thing that happens with metals like iron is that when they lose electrons to produce cations, there's the 4s sublevel, the 4s orbital empties before 3d, which is kind of unexpected. For example, iron 2 plus would have 24 electrons because it has lost 2 electrons to gain a charge of 2 plus in relation to the 26 electrons that are in the 26 protons rather in the nucleus. So if I want to write its electron configuration, I'm going to encounter this kind of surprising result that the 4s orbital is the one that empties out and the 3d subshell remains full. So the 2 electrons that are lost to make that ion are actually lost from the 4s orbital. This is just a more energetically favorable way for a lot of transition metals to ionize, to empty out the s orbital first. The final thing I want to mention is that you can abbreviate electron configurations so you don't have to write out the whole thing all the time, which is kind of nice. For example, chlorine's electron configuration, I could abbreviate it as, okay, let's find chlorine in the periodic table here. What you want to do is you go up to the nearest noble gas above it, and you can put brackets around that noble gas. So for chlorine, it would be neon. And then you just write the electron configuration for what's called the valence shells. So in that case, for chlorine, it would be 3s2, 3p5. So this is an abbreviation that means exactly the same thing as the electron configuration that we wrote up here. It's just basically taking this bit of it and saying, this is the electron configuration of neon. And then here we just have the valence. Let me show you for iron. We can do the same thing. Iron is down here. The noble gas above it is argon. So I can say electron configuration of argon, and then the valence shell, which is, oh, I guess I'm looking at the ion, so I should be looking up here. The valence shell for neutral ion would be 4s2, 3d6. Okay, because if I'm looking at just this whole bit here, that can be covered by saying the electron configuration of argon. All right, so that helps, especially with larger elements, because you won't have to write out this big long string of an electron configuration.